Okay, good afternoon, everybody, and it's my pleasure to chair today's lecture to be given by Professor Bjorn Stevens from the Max Planck Institute. And so we'll proceed as the following. We'll have a lecture first, and then there will be opening for discussions. Bjorn especially like to have questions, I guess, and the topic today is also very broad and can be, I think, useful to many of you. And I also guess that you have many questions or to discuss with our speaker today. So then after that, we have the interaction session. We have actually a photo together, and I will guide you about how to do this. Before the lecture, I would like to really introduce our speaker today more formally. So Professor Bjorn Stevens is a world-renowned atmospheric scientist and a director of the Max Planck Institute for Meteorology in Hamburg, Germany. His research focuses on improving our understanding of how clouds and atmospheric processes shape Earth's climate, which is essential for making reliable climate projections. He is also a professor at the University of Hamburg and is actively involved in major international climate research initiatives. Among others, he has led the initiative, the Earth Visualization Engine, EVI, short-named, an ambitious effort to develop a new generation of global kilometer-scale Earth system models. And it has been a key contributor to shaping the EU's digital Earth, digital twin Earth, and destination Earth strategies. Professor Stevens is an AGU member, a fellow, a member of the Max Planck Society, and a joint lead coordinator of the World Climate Research Program's Grand Challenge on Clouds, Circulation, and Climate Sensitivity. As you all know, that climate change is a defining challenge we all facing, and cloud and atmospheric science and processes, including the fine resolution climate modeling, is really the key, I would say, to the climate research, and also impacts and many other downstream applications. So Professor Bjorn Stevens today will give a talk on climate modeling, and basically from his experience as an atmospheric scientist, and with a special emphasis on the so-called cloud resolving modeling, I guess. And so, Bjorn, the word is yours.
So I didn't realize that this Python color scale thing, say, wow, this is very nice. It's really a pleasure to be here. So thank you very much for the invitation. Everyone has heard of Tsinghua University. Whenever we get an applicant from Tsinghua University, we're like, oh, we have to look at this very closely. So it's really one of the great universities in the world, and it's my first time here. I've been to Beijing several times before, but never to Tsinghua. So it's a pleasure to see the university firsthand. And so, yeah, thank you very much, and thank you for that kind introduction. Today I'm going to talk about climate modeling in a new era. And I think it's useful to, once in a while, try to think about what makes one thing different from another, to draw distinctions, even though when we distinguish between human creations, they'll end up being artificial and maybe exaggerated. So I thought in this lecture I wanted to give you my view on climate modeling, why we develop and use climate models, and show you some of the frontiers of the field as far as I see them. And I will introduce what I will claim is a new class of models, and I will say why I think they're a new class of models. I'll try to distinguish for you the difference between modeling and simulation so you can understand some of these distinctions. And for the new class of models, I will try to bring out what I call 8 superpowers. I was told 8 is a good number. It's funny how you make a good number out of 2 bad numbers. So it is true, right? 4 plus 4 is 8. And so I will talk about the 8 superpowers, and then 2 curses that make the models a bit problematic. This actually is a nice way to think about most of the history of climate modeling. It's a dot, a line, another line, and an area. And that describes geometrically how we think about climate models through most of their development. They've largely been either a simple balance at a point where there's no spatial variability. They might have looked at variability in the vertical. Those two models sort of go together in what we'll call energy balance models. They have that sort of geometry. There's an extension of those in the meridional direction, which have been related to energy balance models, but we'll go a bit beyond that. And then there's these quasi two-dimensional models, which are really what the modern, people don't present it like that, but essentially the sort of traditional climate models that we've used over the last decades to make many reports for the IPCC and things like that kind of fit into this other category of model. So I'm going to try to explain that and then introduce what I think are a new quality of models. If we go to the 0D model, it's really just about an energy balance. I think I don't know how you can see that. You can see that here. You know, an energy balance model would be a very simple model that you learn in high school, where you look at the amount of sunlight coming into the surface. So with the solar constant, you reflect some of it backwards. And then at the surface, you would, I wonder if it works better here to, can you see that okay? I think, whoops, I don't want to go there. Yeah. This doesn't, oh, I'm pushing the wrong button always. No, I have it. I think, let's try that again. But
oh, yeah. I don't think it's working on this screen.
It doesn't work. Okay,
Yeah.
so I'm going to just refer to the screen and hope that you know where I'm looking at. But if you look at the left and you just look at the black line, then you see the solar energy coming in, some of it would be reflected out, and then you lose infrared energy from the surface. If you had no atmosphere, and you look at the balance of energy going in and out of the system, that would be sort of a zero-dimensional model, and that's where many of us start conceptualizing the climate system. A famous model, which we'll come to later, Boudico, used this approach locally, and Arrhenius also used this approach locally when he made the very first climate model. And the purpose of that model of Arrhenius was to try to understand the ice ages. So we build models because we have a question. So Arrhenius was puzzled by, this was 1896 in his first model, and his later model was 1901. And he was puzzled by the fact that there seemed to be geological evidence for the Earth being covered over large regions by ice, which suggested that it was much colder at one time. And he suggested that maybe these ice ages could be caused by increases in CO2. And to demonstrate that, he made this zero-dimensional model where he looked at just the energy flux into the surface and out of the surface as mediated by the atmosphere. So you could think of that as a zero-dimensional model, or maybe a one-dimensional model, which is shown here, where you actually have some representation of the role of the atmosphere in the model. This model here is Manabe's model. So this was, if I go back one here, yeah, this model here is a representation of Manabe's model, which I would say 70 years later solved Arrhenius's problem. So Arrhenius tried to model this. The way he treated radiative transfer was hugely disputed. People forgot about it. People rediscovered it. People tried to do the radiant energy transfer differently. People looked at the problem from the point of view of the surface energy balance. And only in the 1960s, when Manabe began to have a more sophisticated view of the spectroscopy of water vapor and CO2, and he took the view of looking at the atmosphere from the top of the atmosphere. So he looked down at the surface and he said, well, how much energy is flowing into the system, the net radiation into the system from the sun? That's what goes into the sun minus what comes out. And what comes out in the infrared? There he found that if you did it this way, the problem becomes much simpler, because the atmosphere mostly controls how much infrared radiation leaves from the surface. The atmosphere is cooling because of its greenhouse effect. And he showed that in order to get a stable solution, you had to transfer energy from the surface into the atmosphere via convection. And that led to this idea of radiative convective equilibrium. And it's shown on the left there by that little gray cloud. In his model, he he simulated how the radiation would go through the atmosphere, how it would be emitted by the surface, how it would be absorbed by the atmosphere, how it would be re-emitted by the atmosphere. This was all based on fairly solid physical principles, but doing that led to an atmosphere which was unstable. And it was cooling so that the atmosphere above the surface was colder than the surface, which was gravitationally unstable. And he realized that to balance the system, he needed a way to get heat from the surface into the atmosphere. And then the posit was that convection restored the atmosphere to some critical lapse rate, 6.5 Kelvin per kilometer. So there he modeled a bunch of physical processes to, he just made something up. He said the atmosphere wants to maintain a critical lapse rate at 6.5 Kelvin per kilometer. And you can see that's a diagram which we colored, but that's from Manabe's original paper, a little bit annotated. And it shows the calculation at 3 different levels of CO2. And it shows that when you increase CO2, the atmosphere warms at levels below its minimum temperature, and it cools at levels above the minimum temperature. So above 15 kilometers is the stratosphere, which cools. Below 15 kilometers is the troposphere, which warms. Below 15 kilometers, the convective heat transport is important. You have radiative convective equilibrium. Above 15 kilometers, convective heat transport's not important. You have radiative equilibrium. And in radiative equilibrium, an increase of CO2 leads to a cooling. And in radiative convective equilibrium, it leads to a warming. And you can see that the lapse rate in the lower atmosphere is held constant. And that's the modeling of the convective heat transport. So you could say that with this very simple model, which mimicked some simulation of radiant energy transport and modeling of convective processes, he was able to solve Arrhenius's problem. It took 70 years, but he did it. And I think no one's really questioned this basic idea since that time. In fact, we've gone a bit further, and that's shown here. In the last years, there's a group of people. One very influential person is a guy named Daniel Cole. He teaches at Peking University. He did this work while he was at Harvard on a postdoc. But his work and a few other people's work, I've been involved in this as well, has shown how you can really understand Manabe's work just by understanding the spectroscopy of water vapor. And this shows the spectroscopy of water vapor as a function of frequency, or actually wave number, but wave number behaves like frequency, so higher frequencies are to the right, lower frequencies are to the left. And the blue line is the absorption coefficient of water vapor, and you see it varies by almost 6 orders of magnitude from the low wave numbers to the moderate wave numbers. And so if you think about that, 6 orders of magnitude, it tells you how absorptive water vapor is. So now imagine yourself, you're in outer space, and this is Earth, and there's an atmosphere in front of you. And you're thinking about infrared radiation. So if you have goggles on where you look at the very low frequencies or the low wave numbers, the atmosphere will be absorptive where water it will be absorbing where water vapor is absorptive. So at these low wave numbers, you won't see the surface. You'll just see a gaseous planet. As you increase the wave number in your goggles and you tune them, you'll see deeper and deeper into the atmosphere because you have to go further and further into the atmosphere before it becomes optically thick. And eventually, there's a few wave numbers where the atmosphere is sufficiently transparent that you could actually see all the way to the surface. And then as you get to yet higher wave numbers or frequency, again, the surface goes away from your sight because the atmosphere becomes optically thick. So everywhere above that dashed line, the atmosphere is optically thick in the thermal infrared. Forget about the CO2 line there just for a second. And where the atmosphere is optically thick, it tells you that water vapor is controlling the radiation. And if you make the one very simple assumption that relative humidity is constant, what it tells you is that the atmosphere at any given wave number will always become optically thick at the same temperature. What that means is if you warm the atmosphere, the temperature at which the atmosphere becomes optically thick won't change. And so when you heat up the surface of the Earth, the only place you will see the radiation being emitted is more or less in that window region there. And what you can do is you can integrate over that spectrum and you can find out where is the atmosphere optically thin. If relative humidity is constant, we won't see any change in radiation. And what you find is that the response of the Planck function to warming only happens in that window where the atmosphere is optically thin. And from that, you can calculate almost by hand the Manabe numbers that he did in his radiative calculation. So today, for this atmosphere, if we forget about clouds for a second, we can calculate almost by hand, almost from quantum mechanics, from the absorption spectra of CO2 and from water vapor. We can make a very simple model, and we can calculate that the climate sensitivity, forgetting about clouds, would be about 2 watts per square meter. This is often people talk about this as a water vapor feedback, but it's not a feedback. It's just the fact that water vapor is masking the radiative response of the surface over most of the thermal infrared, and the radiation is only happening over a portion of the spectrum. And so there's a series of papers which have worked this out, and it gives you a very intuitive feel of how the atmospheric works. But you have to be able to think in wave number space. You have to think of the atmosphere colorfully, that it radiates energy at many frequencies. Some of those frequencies respond to warming, and some of those don't. And from this point of view, we have a very deep understanding of how the greenhouse effect works, and it gives us a lot of confidence that the models are behaving sensibly when we make more complicated models. But I guess the point I wanted to make here was that we solved this problem by using simulation of radiant energy transfer for the radiant energy. And in a way, we modeled what was happening in the atmosphere by making, in this case, just a very simple assumption that the relative humidity was constant. That's something we made up. That's something we modeled. And if you think about climate sensitivity more generally, you can say here that the climate sensitivity depends on the forcing. Using those same arguments about what becomes optically thick and what doesn't become optically thick, you can calculate by hand what the radiative forcing would be. So you can calculate the forcing F. The climate sensitivity is how much the surface would warm for a doubling of CO2. And lambda is the radiative response. So if you imagined a black body responding, then you would say lambda is equal to 4 sigma t to the fourth. And d lambda dt, not d lambda, the radiative response would be sigma t to the fourth, and the change in the radiative response with respect to temperature, which we call lambda, would be the derivative of that. That's 4 sigma t to the cubed. And you can see right away that 4 sigma t to the cubed is 4, about. You could calculate that, right? Because you know, how would you calculate that? Do you know what sigma t to the fourth is? Sigma t to the fourth is about, we know that's about the radiation that comes out of the Earth. That's about 240 watts per square meter. So sigma t to the fourth is 240 watts per square meter. That's what needs to leave the surface. Sigma t to the fourth divided by t is sigma t cubed. So 240 divided by t, 255, is 240 divided by t. So that's about 1, and there's a 4 in there. So you could just do that by hand, and you can see that the radiative response function is about 4, and that gives you a climate sensitivity. If the forcing is 4 and the response is a black body, it gives you a 4. So you get a climate sensitivity of about 1. Now, if you say, well, actually, it's not a black body, but most of the spectral response is masked, like we did before, you can calculate almost by hand. You'd have to add a lot, but you just integrate over those wave numbers, and you get lambda is equal to 2. And that means your climate sensitivity is twice what you would expect it. Instead of being a climate sensitivity of 1, which is just from the black body, you get a climate sensitivity of 2, because much of the radiative response is masked by the relative humidity assumption. And then it's not very hard to say, well, it's not only the thermal infrared. We know very empirically that as we warm the planet, surface ice goes away. And as surface ice goes away, we can just calculate empirically what that is. And that's another half a watt per square meter per Kelvin. And you get very closely to about 2.8 for the climate sensitivity parameter. So making very simple arguments and using this mixture between radiative transfer theory and simulation and modeling, you can figure out what the climate sensitivity is. This all depended critically on an assumption that the relative humidity was constant. And recently we went to a place on Earth where we most expect to observe global warming, and that's over the ocean in the tropics, where we have deep convection away from regions that are affected by El Nino and interannual variability. And it's a place where we have measurements from 50 years ago from a giant field campaign called GATE. And 2 summers ago, in 2024, we went back and made measurements with an aircraft and measured that area again. We had thousands of radiosondes going up and down through the atmosphere. And we asked ourselves, does the relative humidity stay constant? Here, the y-axis is temperature. temperature is like height. When the temperature gets colder, you go higher in the atmosphere. The theory that we need for global warming is that the relative humidity should not change with temperature. So we plotted it. We looked after 1.5 degrees warming over 50 years in a 2-month period in the place where we would most expect to find global warming. And we asked, did the relative humidity stay constant with temperature? And that's the difference between the blue and the orange line. So it's stunning how similar those two curves look. And they don't have to look similar at all. If I just took 2 places on Earth and plotted the relative humidity, they could be very, very different. But the relative humidity, and it's also not a trivial curve. There's a lot of structure in the lower troposphere. It's simpler in the upper troposphere. But what we were able to show is that indeed this assumption that's really at the heart of our understanding of global warming, it's the assumption that we use in the model, is well represented. Unfortunately, so we've worked out using simple models and simulation of radiant energy transfer that how global warming works. But we had to make not only assumption that relative humidity is constant, we had to assume that clouds don't vary. And it turns out that when we put clouds into the problem, a small change in cloud can have a large change in the climate sensitivity. So clouds still need to be modeled. We need to somehow make up rules for how clouds will change as the Earth warms. And those will be connected to how moist convection behaves. So in this very simple picture of climate, clouds are what we call the joker or the wild card. We still don't know what they do. And until recently, maybe until a few months ago, if you had asked me, I would say there's really little evidence that clouds are doing very much. That's changing. I mean, there's a new series of measurements over the last 20 years which we're bringing together, which actually suggests clouds are changing in ways that we don't understand. But if you just put that aside, because that's not really worked out science for the moment, if clouds don't change, I think we have a really good feeling of why the climate sensitivity is 2 plus the change in surface ice, which gets us to a number that's pretty close to 3, the canonical climate sensitivity number of 3 Kelvin. Good, okay, so that was all worked out in without saying anything about continents or poles or variations in other parameters. There's no Tibetan Plateau, there's no Greenland, there's no Antarctic ice sheet. And after Manabe published his work, another very influential study came out, which was by a guy named Boudico. And Boudico looked at the Earth like this. So just as a function of north-south. His model really had no vertical. And what he showed was what I was saying, this ice albedo feedback, was that as you warm the planet, if you have an equator and a pole, the pole can be quite cold and support surface ice. And as you warm the system, then the surface ice in the polar regions will decrease, or if you cool the system, it will increase. So that introduces this thing called the surface albedo feedback. And he just made a very simple model of it like this. You can calculate what that is empirically, and that's where I said the climate sensitivity is about 3. It's 8/3 is what you get if you get a simple estimate of the surface albedo feedback empirically. But he again, this, when you look at this, it's a bunch of arrows and sketches. It's a model. So people are saying radiation behaves like this, heat transport goes like this. The big thing is the red arrow. In his model, he said some of the energy that goes into the tropics gets exported to the pole. And he just made up a rule for how that works. He said, well, let's let it be based on the temperature difference between the pole and the equator. That's a very reasonable rule. Let's let it be diffusive. Sounds also reasonable because the mixing processes are small compared to the scale of the Earth. But again, it's just something he made up that sounds reasonable. That's a model. That motivated Manabe to go back to the drawing board and get rid of his sort of one-dimensional model and say, you know, maybe I have to worry about continents, and maybe I have to worry about ocean, and maybe I have to worry about latitude. And if you look at Manabe's paper in 1975, he said exactly that. He said, Boudico made this model where you had heat transport from the equator to the pole. Maybe that's important for my climate model, so I'm not satisfied with this sort of 0 or one-dimensional theory. I would like to represent it in more dimensions. So he constructed a problem like this. This was Manabe's Earth in the 1970s. It's from his paper. The gray is the land area. it goes from the equator to about, I think it went to about 80 degrees or 75 degrees, not all the way to the pole, because that would be a singular point that was hard to treat numerically. You had an ocean region that looked more like the Southern Ocean, and you had a bunch of land. And he said, what we can do, we don't have to model the heat transport. We can use this emerging ability to simulate the heat transport using the equations of fluid dynamics. So about 10 years before, a guy named Norman Phillips had shown that you could discretize the equations and you could simulate baroclinic eddies breaking and the heat transport from north to south. And this is shown here. If you take Manabe's model, these are figures from Phillips' paper in 1956. And what you see are patterns of highs and lows. And what I've done is I've taken the different panels from that paper and I overlay them. And so you can see the temperature gradients in the dotted lines and the surface pressures in the solid lines. And you'll see these highs and lows moving through the system. They move from west to east. They're associated with the warm fronts, which you see here. And the cold air coming down here. So you see the flow around the low going like this. And this would be the basis of storms that form in the mid-latitudes that do what Bedico just made up. So you see Manabe saying, okay, we have this problem. We want to understand global warming. We have this 1D thing. Seems to work pretty good. We don't know how to calculate the surface albedo feedback. The transport to the high latitudes might be important. Bedico made it up. Let's see if we can simulate it. So he applied these methods, and this is how the lows and things moved in Phillips' model. So Phillips basically showed with this is the grid space thing. That's one grid element to calculate these fields. So it was a multi-level model. So it was a baroclinic model, and he could simulate the instabilities. And Manabe ended up, after a period of, in his original model, he got a lot of insight from simulating in that geometry on the upper right. But over the time, he tried to give it a more realistic geometry with more realistic continents. And by the 1980s, he was applying these Phillips-like methods in a fully, you could say, a fully more globally realistic context. So this is a coarse resolution climate model. It's not actually that different than models that people use today in projects like CMIP. It's a little bit coarser resolution. So this is T31. The models used today on average have about twice the resolution. There's much finer ones, but it still has this principle, and I'm going to go over here and show you. You see the eddies here. These are these Phillips eddies that Bedico had to parameterize their model, and they go from the west to the east. And associated with this is OLR, and you see precipitation in the blue, and it shows you how the energy of the tropics that's accumulating is being carried to the pole. And you see the same thing up here. You see something else in the tropics. It just looks like, it's a bit spastic. So if you look in the tropics, blah, 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 blah. It's just, it doesn't look like the tropics that you would normally expect to see, except that it's finer scale. You don't really, if anything, you might see some tropical systems. Here's South America, you can see in the red, so you see a concentration of precipitation that blinks on and off, maybe with the vernal cycle. You might see a hint of IPCC here. But all through the tropics here, the atmosphere is behaving differently. It's not behaving like Phillips. It's not a quasi-two-dimensional atmosphere. So in Manabe's models and all the general circulation models that have existed until recently, the atmosphere was treated as a series of very thin two-dimensional layers, and they were coupled in the vertical statistically in the same way Manabe did in his original model. So he said, let's just relax the atmosphere to some prescribed profile. And people did that more or less elaborately, but he wasn't simulating, he was modeling. He was making up rules for how to connect the different vertical layers, whereas in the extratropics, he was simulating with the equations of fluid dynamics. So the hypothesis here was that if you get the eddies right, if you have the continents to kind of make a thermal contrast that induces large-scale two-dimensional Rossby waves, then the tropics would just kind of go along with the thing and be okay, and you could use these simple methods. And it turned out that this was enough to get a fairly a somewhat clearer picture of how the atmosphere worked. And already in these early, late 1970s, early 1980s paper, here you can see again blue above red, so the stratosphere is cooling, the troposphere is warming. But what you also see is that the warming, the zero line is here. So everything here is red, like we saw before in that one figure. And this is from Manabe's paper. I think this one is, sorry, that's the wrong reference. This is Manabe's paper in about 1975. And what you see is this is the North Pole, and that's the equator. You see what we call the polar amplification. So we already see in this work the polar amplification. He could show that this type of model predicted that the land would warm more than the ocean. It predicted the different depth of the troposphere. So a lot of what we take to be true about climate change seem to emerge from this model, which its key advancement relative to the earlier models was to have this land-sea geometry, to have this north-south gradients in insolation on a spinning Earth, and an ability to transfer via these quasi-two-dimensional baroclinic storms and eddies energy from the equator to the pole. And I would say out of this, you have these sort of two famous classes of climate models. You have energy balance models, which might or might not have an atmosphere, but they make no statement about what's happening at the surface. And they might have a thin ocean and a deep ocean. But this would be an energy balance model. We still use these today. These sort of models are really influential. These sort of models are quite influential in the IPCC because they're used to interpret a two-layer model with a prescribed behavior of the atmosphere, are used to interpret the global behavior of much more complex models. So these are very much used today. You have models here where we have in the atmosphere, we're simulating the, these are supposed to be two-dimensional levels, and we're kind of simulating the quasi-two-dimensional flow in different layers, and then we're modeling how the heat transport happens in the vertical. So how convection moves moisture through the vertical and how that interacts with radiation. We also include an ocean, a laminar ocean, which is circulating. So we might have an overturning ocean. You see that here as well. So the ocean models would have an ocean circulation. The ocean in an ocean model is somewhere between, in a modern GCM, like you will have in CMIP or IPCC, it's somewhere between tar and honey in terms of its viscosity. So it's a very laminar ocean. But you can simulate that ocean for very long periods of time and try to understand how the cold waters or the dense waters of the deep ocean form, how that relates to the pole, the equator heat transport. And that leads to also what happened was this intermediate model that's sort of between this one and this one. Because the ocean is so slow, they said, let's not have a complicated atmosphere. Let's have a simple atmosphere. It still has a hydrological cycle, but it doesn't really have clouds. The atmosphere is prescribed. We want to treat the whole atmosphere statistically, like Boudico, but we want to get this ocean circulation. And these models are really quite useful for looking at how carbon flows through the system. So this tells you a little bit about how energy flows through the system. It simulates radiant energy exchange. This one has a radiant energy exchange, and it simulates a laminar ocean, but everything else is sort of parameterized. And this is 2 steps forward because it has these two things, but it also gives you the instabilities of a zonal current and the large-scale waves and responses to heating associated with topography and continental geography. So each one of these are different classes of models. They're different classes because they simulate, they replace assumptions by basic laws of physics. They're more advanced and they allow you to solve different types of problems. But there's some problems, this is a more physical model, that it's just, you can't compute because the ice ages, for instance. If you want to look at the coming and going of the ice ages, it turns out that the atmosphere is too slow computationally. So you can't have enough grid points to represent how energy flows through the system and advance it far enough in time to simulate the ice ages. So then you have to resort to this. So it's not that the more advanced models can solve more problems. Typically they solve fewer problems, but they solve them in a better way. So these are 3 classes of models. People who make these are very proud of them because they were the latest ones. And they try to use these to do everything. I think in the latest round of IPCC, these are actually much more suited for some of the questions people are asking. But yeah, that's things scientists can argue about. So here, I've said it a number of times, but I wanted to put it on one slide, modeling versus simulation. And there's this nice quote from a leader in turbulence research. So if people have friends who work in turbulence, they make this distinction all the time. And the distinction is that modeling and simulation is different. Modeling is a mixture of analysis, empiricism, and analogy directed to rather practical aims. So when we talk about modeling, we really mean that we're making up relationships based on, informed look at how the world works. But it's not fundamental physics. So if you look at a GCM or a modern climate model, there'll be some equations, 6 or 8 equations, that are the same in every model. Those are the equations that we believe. But there'll be 2,000 equations, which everyone does differently. How the snow albedo works, how the forest works, how the land water is accumulated. People all have little differences or big differences in those equations. Those are the modeling. And a climate model is a mix between basic physics, it tends to be a fairly small part, and modeling. And knowing what that mix is quite helpful. So I would say some remarks here in this mid-stage, and the remarks would be that the first thing is we got really far in understanding climate just by understanding the vertical energy exchange. I mean, we solved most of the problem with Manabe and Weatherald in 1967, and it's primarily a question of how the atmosphere mediates energy exchange in the thermal infrared and the visible, and secondarily, how that energy is exchanged between the low latitudes and the high latitudes. Early climate models, like Manabe's, were developed by combining models of vertical energy and matter exchange with simulations of the quasi-two-dimensional planetary scale dynamics that transferred heat from the pole to the equator. When you did it this way, you have these two challenges, is that you need to make the model behave right on average, and you have to do that by whatever part of the circulation in the model, the winds as they blow, you have to make the clouds respond to that properly, the water vapor respond to that properly, the rain respond to that sort of properly. And this is normally just done by fitting. So when people develop a climate model, they come up with their best idea, they put it in the model, and then they look at how the model does, and they see something they don't like, and then they change and fiddle with it until it behaves about right, and then they keep it. And if they put something new and the model behaves badly, then they either take it out or work. And I think one of the things our community doesn't do enough, and it gets in the way of progress, is we don't really acknowledge that a large part of climate modeling in this class has been based on fitting these statistical models to what we know about the climate system. And then we run them forward. So in a way, the climate models we use aren't that different than machine learning. We're just kind of fitting a bunch of statistical parameterizations which are based on physical ideas to the data. They're not really constrained a priori. And the way we get around that is we just let people choose different strategies for fitting, and then we compare them a lot. So here's this picture again that these are the different climate models. And now I want to make a break and say, there's a curious thing that's going on here. So here we are, so stop for a second, recalibrate our minds. We've seen this sort of sweep of the development of climate models from the very earliest models to modern models. And if you look at the years in which we're there, we see that this early model had 544 points. This is on with 40-bit words. The next one had 4,212. This one had 20,000, but this is a factor of 5 over this one. That's 5 years, okay. This is a factor of 10 over this one. That's 20 years. It went up by a factor of 10, went up by a factor of 5 in 5 years. And then we jump here 15 years, and it went up by a factor of 2. And today, we might be in 30 years later, and this might be a factor of 10 more. But if you know anything about computers, that the rate of complexity increase here is small compared to the rate of computing increases. So Moore's law, a doubling of every 1.5 to 2 years, right? So you would expect, you would increase if it's every 1.5 years, and you would expect 3 doublings between here and here. So you would expect 8 times. And you'd expect many, many more doublings between here and here. In fact, what you find is a gain of 2 to the 6 when we could have hoped for a gain of 2 to the 28. So why is it that models, climate models, have been advancing in their computational demands so slowly? The answer people normally give to this is wrong. Normally they do something like this. They show a figure like this and they say, the many dimensions of the climate problem. So it's not just about spatially resolving the flow and better simulating the physics, but we have to deal with, process complexity. So as we move in this direction, we have, biological processes, chemical processes, so we're adding a lot of complexity to the model. We don't really know what the future looks like, so we have to explore a lot of scenarios, the scenario diversity. And in the end, the climate's variable, so we want to quantify ensemble variability, so we have to sample all of these dimensions by running models in large ensembles and perturbing parameters. And that's just, all of these dimensions compete with the idea of running the models at higher resolution. Hence, what we're trying to do in the climate community, people will often say, is balance the competing demands of complexity, scenario variability, ensemble, the need for ensembles with spatial temporal complexity. And the reason that answer is wrong is that all of these dimensions are relatively easy to sample. They're all algebraic. That means if you look at a scenario, you go, you can double the number of scenarios and you double the cost of the computing. The problem with this dimension is it's hard, is that when you change the resolution, you change it in 3 dimensions for it to be effective, and you have to change the time step. So if you double the resolution, you have 2 to the 4th increase in complexity. So moving up this axis is very painful computationally, and moving along these axes are very easy. Moving along these axes, you can do in a very distributed manner. You can run a scenario on the computer in Tsinghua, you can run another one in Peking, you can run another one in Fudan, you can run another one at, all over. So this scales wonderfully. It's perfectly parallel. This is perfectly parallel. You can distribute this over many, many computers. This, you can explore different processes over many computers. So all these dimensions are relatively easy. Only this one do you need a big computer that's all connected with a big interconnect fabric that works coherently together. So that dimension is hard. So the real reason we haven't been advancing in complexity is A, that doing so is very difficult, and B, that new processes that we want to simulate happen at a scale that's very far from the old ones. So to simulate the heat transport from the equator to the pole, we needed to simulate eddies which were many, many hundreds of kilometers across. We didn't need a very fine grid. You saw that the Phillips did this with these little rectangles, 512 of them. The scale of poleward energy transport is large, and the atmosphere is thin. So if we want to really advance simulation and bring in a new process, it really only happens when we get the instabilities in the vertical, the ones that control the 3-dimensionality of the tropical climate, these violent thunderstorms that bring energy upwards into the atmosphere, that organize into mesoscale convective systems, that when there's enough rotation form typhoons that cluster in large tropical waves that form across the tropics, that form the Mayu that will, I don't know, do you feel the Mayu here in June? Does it come this far? But certainly in Shanghai and in Tokyo, these processes which govern that happen due to instabilities which happen in the vertical, and the vertical is 10 to 20 kilometers. So if you want to simulate something new, you have to get a lot. You have to go from something to resolve something that's 1,000 kilometers to something that's 10 kilometers. It's a factor of 100, and you have to raise it to the 3rd or 4th power. So the gap you had to go was enormous. So then it really wasn't worth it. So, why double the resolution? Because you really didn't get anything new. You got prettier pictures of things that were old, but you really didn't get new physics until you get to a fine enough scale. And the idea that you could simulate something on this scale seemed absurd, if you look at the computational cost that this would have. So having enough computational power to resolve that seemed hard to believe, and most groups didn't even try. So most groups said, that's not going to happen. We're not even going to try. But a few of us kept trying, and today we can do that. So this is an example of a simulation that we did, about 6-8 months ago, which shows the fully coupled Earth system, carbon, biogeochemistry in the ocean, full representation of the ocean, atmosphere, ozone, clouds. And what you see here is you see clouds of chlorophyll in the ocean responding to productivity. You see eddies off the coast and swirls, see coastal features, and you see clouds of water in the sky. The vegetation is dynamic. So it's a full Earth system model at 1.25 kilometers globally, which shows that you can simulate these things. And here we can kind of look a little bit at how this looks. The vertical dimension here is a bit exaggerated, but you can kind of see it there just for the visualization. So you can see it. So you can see a lot of, we've moved simulation to a new place. It wasn't just that we're simulating this two-dimensional stirring that carries heat from the equator to the pole. We're also simulating the vertical heat transport. You can see that a little bit here in this. I'm going to show you a couple of visualizations because I've been talking for a long time and it's nice to have some nice pictures. Here's another example. This is this large-scale cluster of clouds, which you very rarely would see in a traditional climate model. And you just see the power of the convection over the coasts will go into the night. We prepared this for a talk I gave at the Shanghai Forum. So sorry, no offense to you in Beijing, but we zoomed in on Shanghai there. So I can do that one more time and you can kind of have a picture of that. And so what we're looking here is we're seeing clouds on the one hand and wind speed on the other. So the colored is the wind speed. So you see these real jets around coastal features or between islands. Here you can see in the straits here that you see enhanced flow. And then sometimes also in the later one, I'll do a couple other views of this. This is another way of looking at it. So in the top, what we see is clouds and rain kind of just zooming in, and then you can go in. So it's a global simulation, but we're just doing a cutout so you can see some features a little bit better with leaf area index. This is South America in the middle, and here we see the currents, the equatorial currents kind of with the dashed, and the chlorophyll in the white. And you see the beauty and the complexity of all the scales that contribute to the Earth system. And here we're actually, it's a full carbon cycle. So we're simulating carbon fluxes over the Southern Ocean and ocean currents, which are sort of emphasized here by a bit of color. So it's great fun to even just think about how to visualize everything that's going on here. But it's also a wonderful way to communicate more publicly because people can look at the Earth and they can see an Earth. It's not an abstraction made out of statistical models. They can see one time when we were exploring these simulations, I had a programmer from Colombia, and I said, okay, your job is to make a plot at a hackathon. 2 days later, I went back to him. I said, what do you make a plot of? And he said, I wanted to go in Colombia. I always go fishing in this place, and I wanted to look at the chlorophyll where I go fishing. But you could do that, So he went, and it actually made sense to him. That's over here. But people see things that they're used to seeing, and you see the effects of river valleys and orography and the Lee. So you're simulating the atmosphere because you're physically representing how things work. I wonder if I come here, I wanted to make one other point here, is that people say this is way too expensive. And it is computationally expensive. To do these simulations, we use the largest computer that we have in Europe, an exascale machine. There's larger machines now in China, but it's a big machine for Europe. We could simulate on this machine, these simulations, they're 2.5 kilometers. They're not one like the last one, but we can simulate 700 years a year. If you gave me that machine, I could put a throughput of 700 years in 1 year. So I could simulate 100 years 7 times. I could simulate 50 years 14 times. If I had the machine for 2 years, I could do it twice as much. Any given machine tends to live 5 or 6 years. So we're talking about 4,000 years of simulation capacity for this giant machine. could you think of a better use for a giant machine than that? You know, if you think what people use these machines for, is there anything better to use that sort of machine for? Maybe making medicines, if they're good at it. Maybe making some new materials. Those are good uses. But a really good use of a machine like that would be to help us look into what the world might look like in the future more physically. So people say it's too expensive, but really what they're saying is it's not really important. Because if it was important, we wouldn't hesitate for a second to use these sort of things. So I think there's a danger when we say, oh, that's too expensive. It's kind of telling the world that, oh, it doesn't really matter that much. So I don't think it's too expensive. You can do a lot, but you also have another problem here, is that the data becomes a problem. So for every year, I create 150 petabytes. 150 petabytes, okay, you can manage that a little bit to write it, but try to read it again. Try to make a plot again. So in a way, this is a bigger problem than that, but they're both problems. They're both the two related to the two curses, which I'll come to shortly. Let's see here. So I said I have to, one of the problems with these videos is it won't switch until everyone gets started. There. I'll give a talk at CMA tomorrow. By the end of the decade, by 2030, I think we'll be able to simulate that whole thing at 100 meters. So we've worked that out. I think we can do that. We won't be able to simulate for years, and we'll come to that. But we'll be able to simulate 100 meters. And 100 meters, this isn't global, but 100 meters allows you to look at something that looks like this. This is all over Germany for some prototypes. But the clouds become much more realistic. You can see shallow cloud regimes. You can see the differences between different cloud layers and how they interact. And so this is the sort of capacity we have now to simulate the things that people used to model. But before we get there, I want to talk about one of the curses we have about computing, and it's really the curse of time. And the curse of time is shown here. So this is resolution, coarse resolution, fine resolution. And this is what we call temporal compression. So 10 to the 0 is 1. So that means it takes me 1 day to simulate a day. Might as well just wait. This is resolution here. And on any given machine, this is the limit of what it can compute. So if I have a given machine with a certain capacity, I can simulate coarse resolution at 100 days a day, or I can simulate finer resolution at a few days a day. And as the machines get bigger, because of Moore's law, this blue line moves this way. The problem is you can't always, when you take as the blue line leaves this way, you could say, I could simulate at 100 kilometers 1,000,000 days a day. But often you can't do that because you can't parallelize the model on the computer as fine. And so what happens is you only can use the computer efficiently up to here. And so as a practical, this is called the strong scaling limit. As you get beyond here, it doesn't make sense to try to discretize, to parallelize your model further and use all of this capacity. It makes more sense to run ensembles or process studies or scenarios. And the biggest calculation you would do in this. So then if you want to use this machine, the only way to really use this machine for resolution is to move down this line. But the problem with this line is it's sloped. So as I go to finer scales, it's not like I'm going horizontally here. I'm going down, which means as I try to go to finer resolution, I end up having less and less throughput. So the curse of time is the fact that as you go to finer resolution, you have to take more steps to get to the same place. So I'm at finer resolution and I'm one grid point in the model, and I'm trying to get forward in time. And it used to be I could take big steps so I could kind of get there in time fairly quickly. But then when I have fine resolution, the time stepping, which you cannot parallelize, you cannot do that in parallelize, you have to take time steps in sequence. So you have to do like this. And then eventually you have to do like this. So as you go to finer and finer scale, you just don't get anywhere. So there's a real inherent limit out here somewhere that I think we can make models like we're making now. We can simulate a year a day. That's useful. We can simulate 30 years in a month. At 100 meters, we'll be down a factor of 10. So we'd have to simulate, instead of a year a day, we might get 3 days in a day if we're lucky. And even then, the machines, these are the biggest machines, we want to go here. These machines really aren't allowing us to do that quite effectively. So there's a real computational barrier that exists. The world isn't just going to allow us, we're not going to get to suddenly simulating the whole world at 100 meters and simulate hundreds of years because computers are so fast. In fact, computers every year get slower and slower. They just have more threads, which means that they can do, it's like if you went shopping, like in a shopping cart. I don't know how shopping is in China. It's like delivery, right? So if you have the delivery service and you wanted shopping and every delivery person can put one thing on their bike, then you'd rather have 1,000 bikes biking your delivery and going fairly slowly, and then you would get a whole bunch of stuff, than having one bike that was fast but had to keep going back and forth because it couldn't carry very much stuff. So you have this multi-threading that goes slower, and it can do bigger computations but not faster computations. And that's limiting things. So these are the two curses, throughput and output. The finer the scale, the less the span. So the finer you do the scale, because of this time-stepping penalty, the less far into the future you can look. So you have to be very clever about how you design your experiments and time slices. And the finer the scale, the more the output. There's another talk I give where I start here. And the beauty here, has anyone heard of Borges's paradox? Or Carroll's mapmaker's dilemma? I talked about this in the Shanghai thing. There's this old story where you imagine a map maker who makes a map of the kingdom. Maybe the emperor says, make a map of the kingdom, and make it in as much detail. And so they make a map which is this big, and the whole kingdom fits on it. And he's like, I can't really see where Beijing is, so let's make it this big. And then eventually they make a map that's so big that you can see every detail, but it's as big as the kingdom itself. And then they have the problem that they were not allowed to use the map, because when they try to open it, it covers the kingdom. And they figure, well, that's no good. And we have that mapmaker's paradox here, is the output becomes so large that we can't look at it. The beauty of AI is that its ability to compress information. So the real thing that's changed, this curse has been, in a way, resolved, because AI, you can think of it figuratively. If the mapmaker could go into a different dimension, open the map, figure out what you wanted, go out of that dimension and say, oh, that's how it is, that's where you want to go. But that's what we do every day here, right? We open a map in a different dimension, in a digital dimension, and we look at immense amounts of information, and that AI solves this problem. It doesn't solve this problem. So those are the two curses. Anyway, that brings us to what I would say a new class of models, global storm resolving or global LES models, which include additional physical processes, which is why they're rain and cloud formation. And what I didn't mention is that before we had this laminar ocean, suddenly the ocean becomes turbulent. And anybody who knows anything about fluids is that turbulent flows behave different than laminar flows. So we're at an era where we're opening up a whole new world of simulation ability and learning new things. So now I want to get to the 8 superpowers, then I will give you a brief sketch of some of the things we're learning, and then I'll end in about 5 minutes. So the 8 superpowers of these new types of model I've written here. They're more physical, so they rely on laws of nature to a greater degree. There's still things that we model. We don't know how trees work. We don't know how subsurface waters work. We don't know how biogeochemistry works. There's many things which are modeled, so they're not a substitute for reality, but they're better than what we could do before. They're simpler. It turns out that when we use physical equations to represent things, they tend to be a few equations which describe a lot. Whereas when we model things, the equations get very elaborated and complicated. And so in a modern GCM, we have about 1 million lines of code. To do the very complicated calculations I showed before, we only use about 15% of that. The other 85% is for all of these other complicated things that we don't have to do anymore because we're being more physical. Another superpower is that the results are tangible. We look at climate change on a scale that humans can understand. We see winds in straits, we see mountain flows, we see typhoons, we see things that we know and are interested in. We don't have to infer them from something more abstract. We simulate things that we observe. So in the old models, we would represent the average convection, but we never simulate the average convection. We would work in terms of objects, sort of like a fire wouldn't be a real fire, it would be kind of what a fire would do if there were a fire. And now when we simulate scales with winds and we have fire, they can look like real fires or real thunderstorms or real typhoons. They're more easy to test because there's fewer pieces and the pieces make sense individually. So it's easier in a sort of continuous integration development cycle to test components for physical correctness and then just look at what happens when they're integrated. This one's a great one. They might be worse. So the great thing is you go to all of this trouble, you make a model that's much more physical, much more realistic, and the climate's worse. That's pretty cool too, because it tells you you can be wrong. So it really tells you, when you're statistically fitting a model, you never really know when you're overfitting. So here, if it's worse, it really either tells you that you're making, it tells you that somewhere you're making a mistake. And scientifically, this is enormously valuable. So they have more potential to be wrong because there's less fitting involved. They have this nice property is that as you refine a control parameter, in this case resolution, you get closer to the right answer. The old models are designed to work at one particular resolution. If you double the resolution, you have to retune and reconfigure them. Here, the idea is that as you work at a given resolution, as you make it finer, you should get closer to what the right climate is. And if you're not, then something's wrong. And in a very practical sense, why they're cool is that they're solving problems. And let me give you an example of that to conclude, or a couple examples. This is maybe one of the biggest problems of the last 5 or 10 years, I would say, and it's not completely solved. But a really big problem is we know Earth is warming. No one disagrees about that. We know it's because of CO2. No one disagrees about that. But now as the warming is accumulating, what we've seen is that the pattern of warming, which is here, this is 35 years of warming observed, looks different than what the models predicted. These are the old models, the Manabe-like models. So this has been a puzzle. No model that's ever been built looks like this until recently. The first time we ran the ocean eddy resolving, we think that's important, the turbulent ocean model, it did this. This is not that, but if you're trying to simulate that, you'd be a lot happier with this than this. And you can quantify that a bit because you can take, this is the Southeast Pacific and this is the Southern Ocean, and you can make a graph where one axis is the Southern Ocean and the other is the Southeastern Pacific. And you can look at the temperature trends over 35 years. And so this and this are two negative numbers, and that's that point right there. And then you can take every model that's ever been made that you can find and put them in this graph, and you get the gray points, hundreds of gray points. None of them are here. That's what I meant, that this is a big problem. It wasn't just, bad luck. All of the data is way over here. The very, very first time we ran this model in this way, we got that number right there. So suddenly we're out of sample. And when you're out of sample, you're seeing new things. You could say we're lucky, maybe. We were testing different ways if this is statistically just luck, and all the evidence is it's not, because you can look at the internal variability. We weren't able to run many ensembles, but the chance that it was not, this is the 99% envelope of all the models so far. So it's very unlikely that we're lucky. We looked at that in different measures. And so the idea is that there's something that happened in the climate system when we went to higher resolution that made it behave much more physically. We have hypotheses for what that is, but it's not resolved. Maybe one of you guys will figure it out. I think we'll figure it out fairly shortly. There's other examples where it's out of sample. We've been looking at the Amazon deforestation. So if you artificially deforest the Amazon, you reduce evapotranspiration. That's this axis here, it goes down. And when that happens, the precipitation goes down. And so what we've seen these are a bunch of simulations that have been done with regional climate models and global climate models with parameterized convection. And what you find is a fairly strong relationship between evaporation and precipitation. When we go to the scales where the convection is resolved, we're here. So we're again out of sample. And what this means is that you have a big reduction in evaporation, but not much change in precipitation. So how is that? If the water comes from evaporation, how come we don't reduce precipitation? And the answer is the circulation. As you reduce the evaporation, the land heats and it draws much more moisture from the ocean over the Amazon. And so we get a much stronger moisture convergence over the Amazon that compensates for the local loss of evaporation. Maybe that's not right, but every time we resolve run the more physical models, we see a different coupling to the land surface than we see in the parameterized models. So it suggests there's something going on, something to be learned. There's other things that we've seen now. We're kind of collecting results. We see these models have a much more realistic northward shift of the storm tracks and a tilt in the storm tracks in the climatology. This is more difficult. Some models it's true, others it's not, but the interseasonal variability, particularly in the Japanese group who are working on this at the University of Tokyo, is much improved. We get the group at NCAR around Falco-Jute showed that you have much improved tropical variability, not variability, predictability. You can look at, so this got in the New York Times even. It's the first time I know that a Journal of Atmospheric Science paper got featured in a major American newspaper. We have an improved diurnal cycle and we have precipitation extremes that we didn't have before. So the conclusion is that there's a new kid on the block. And it's useful to think about climate models in terms of what problems they can solve, and that leads you fairly quickly to think about different classes of climate models. This class doesn't solve every problem, but it does have some superpowers, and it does have some curses. And we're beginning to use these models to solve some problems that were difficult to solve without them. So that's all I wanted to say about climate modeling, and thanks for your attention.
So any questions or comments? Yes, Professor Tang, go ahead.
I can make the slides available. I've been giving a series of different talks and they kind of unfold around each other, but I will make the slides available so if people want to look at any of the slides. Some when I have movies, I just distribute the slides as a sort of a movie so you can watch the movies play and then you can freeze the movie and take a screenshot if you want the information. But I'll distribute those and for all the hosts, we'll make a folder that people can play with the talks if they like. Yeah.
I will just speak loudly. Thank you very much for the wonderful talk. I have two questions. The first one is I want to know the motivation to run you call this kind of super high resolution model at a 100-meter scale. I think currently our Earth observation perhaps is quite limited to constrain those models. So I really want to understand when we don't have so much observation to even know many things at that scale, what's the main point to simulate at that high resolution? Yeah. Okay, in the past, perhaps we work this at a little bit more coarse resolution, but we can use downscale or coupled with those regional models to resolve this. What's the point to run those 100-meter S-system model at the same time? I mean, of course, a large solution we can use a little bit coarse spatial resolution. However, for some regional, we can do the downscaling things and to get the high resolution. So the question.
That's the first question. I got that one, but okay. Should I? But you can ask sure. The second one, or I'll do the first one and then the second one.
The second one later.
Okay. So there's two answers to that. One answer you probably won't like, but some of you guys might like it, is because we can. And so we think we can, and it's a challenge. And it's a nice challenge, technically, because it forces us to try to explore the real frontiers of technology. And in doing that, we really learn about the technology and about the methods, and we improve almost everything we do. So when you try to do the very most ambitious things, then you do the less ambitious things much better. So in trying to go to 100 meters, we improve everything about the technical workflow that makes everything else seem easy. And so that's good. It's sort of a path-breaking thing. But physically, there's another motivation, and that's for a long time. When I began my career in the 90s, I would run 100-meter or 50-meter, 100-meter large eddy simulation in a doubly periodic box. And I would introduce an aerosol perturbation, and I would look at how the clouds would change. And the idea, I would run it for 3 hours. And the idea was, it was doubly periodic. I would give it an initial condition, kind of like this 1D model, which was based on some observation, kind of idealized. I'd run it for 3 hours. I'd introduce an aerosol, and I'd say, how much did the clouds change? And we convinced ourselves that this was useful for understanding climate change. But of course, you see all of the simplifications we made there. Now I can do that same experiment globally without double periodicity, with realistic conditions, and I could run it for maybe a month. And so looking at two questions. One is, how does the clouds respond to the aerosol? It's sort of the ultimate computational answer. Because it's about the limit of what we'll ever be able to do, I'd like to be first to do it and see what we learn. And then we can see if it makes sense. But we're not going to get any better. So sometimes I call this the computational Hail Mary. So in the United States, there's the American football, the game they play. And in that game, you always have to kind of go, in 4 tries, you have to go 10 meters, like from here to here. And at the end of the game, if you're behind, you have your last chance to kind of get to the far end. And so what they often do is they kind of go back and they take the ball and they just throw it as far as they can and hope somebody catches it. And so sometimes this, for me, is a little bit like a Hail Mary. It's the very last chance you have to try to see what we can computationally compute. And so the aerosol forcing is one of the physical questions. The other is the cloud feedback. So we could do this computation for a month with a cold climate and a warm climate, and we can look globally at how the clouds change. And the problem, you could of course do this regionally. The trick about doing it regionally is you have to decide where. And as soon as then they say, well, why not there? And why not there? Why not there? And why not there? And so if you can try to do it globally, it seems worth doing. So the two answers, one is because we can, and that will increase and improve many things. And the other is that it might, and it's worth trying, it might teach us something more fundamental about some basic processes. But you had another question.
Thank you very much. Then I have the second question. It's about the scale issue. I think now you talk more about the computation limits. But I think when we go to the final resolution, we also, the larger part of the limitation is about the understanding of the process, or the representation of the physical process in the model perhaps will be very challenging. I'm actually working on water cycle. For the land surface model, if the resolution is quite coarse, for example, like 10 kilometer or even 100 kilometer, you know, for the land surface model, even at this time, perhaps you don't describe rivers, lakes, well limited about groundwater, and well limited about the groundwater, surface water interaction, because perhaps those are not that much important when you do the modeling at somehow coarse resolution. However, if you go to 100 kilometer, then those hill slope, you can see it, and then you can see the interaction of surface water and groundwater, and all those processes are not really represented in the current system model. I think I actually attended a meeting at the Ningbo Eastern Institute of Eastern University. We put many scientists from hydrologist field, and we discuss about this. So actually, even now, this resolution, no other hydraulic process is not incorporated into the S-system model. If we go to the value-finding resolution, we think we need to actually incorporate lots of more physical process at the final scale. Yeah. I'm not quite sure for the carbon, for the atmospheric process, but I guess there must be lots of new process. Somehow, even we don't quite understand, needed to incorporate into that model. I don't know how you think about this.
Yeah, no, I think that's what also makes it exciting, because it opens up new frontiers in science. And so one of the things, I think, looking to the future, of course, we won't run 100 meters all the time. That will be kind of one pass we do in one try. But I could imagine the workhorse being this 2.5 kilometer model. And at 2.5 kilometers, you begin to resolve watersheds fairly well, and slopes and river flows. And so at the same time as this project that I was talking about, where we go to 100 meters, what we're also trying to do is work to couple subsurface hydrology. And so we can begin looking at how water flows through the land surface. We can begin looking at slope surfaces to try to understand things like landslide, and we can do it globally. So that's actually an exciting new frontier, because we begin then to try to think about how the land surface behaves on a scale where the processes that affect the land surface begin to be resolved. So when you work at 100 kilometers, you have no representation of the intensity of precipitation. You have no real representation of the watershed and how it collects and funnels water. And so at this scale, we can couple the precipitation to the land surface scale. We can couple the vegetation. You know, in these coarse models, the hydrological cycle and the carbon cycle are fairly decoupled. You know, they have the totally wrong precipitation, but they'll have the right carbon somehow. And so for me, that's also an exciting frontier, is the new processes, but they're physical. The new processes we can begin to think about, and we think about them on scales where we can actually measure them, because we don't really measure the 100 kilometer subsurface. You know, we don't know how to even think about that, but we can measure on the kilometer scale differences. And so I think this could be a very fruitful activity for the science. So you're right, there's many new things, and that's part of the fun. Yeah.
Okay, other questions, especially from students? Yeah, go ahead. Microphone, because we have more than 600 participants online also.
Hi, Professor Stevens. Thank you for interesting content. And I have two quick questions. First one is that, as you mentioned, the computing power and resources increases a lot, and many physical processes can be expectatively resolved. So I wonder, what do you think of the future of parameterizations? Will they still exist, or will they disappear, or be replaced, or it depends on a specific module?
So here is where we get into, I get into some arguments with colleagues. We have different opinions. And there's some people who have been working on the processes that we simulate now. They've been working on parameterizations of how convection works, how cold pools form, how they elevate dust. And these are fun and interesting problems. But the job they've been asked to do is not only to come up with a model of how these things work, but to put that model in another model and harmonize it with many other parameterizations. And I think that task is just unimaginably difficult. We don't know if it has a solution. We don't know if the assumptions make sense. But it doesn't matter. It doesn't mean just because we stop parameterizing things in this model that we stop parameterizing them in our heads. And so in the end, when we want to understand the simulations, we have to develop simple conceptual models that help us understand what's behaving, how the physical system is behaving. So I think it actually makes parameterization a bit more fun, because we focus less on the details of the engineering about how to fit and couple and harmonize that with all the other processes, and more just on the basic ideas about what is this process doing. And then our parameterizations become simpler. So I also like to think that these tools will help us think more physically. And an example of that is if you look at radiative transfer. When we were trying to make radiative transfer models, like Manabe did, he couldn't afford to calculate every line. And so what he tried to do was make a statistical model of the radiative transfer. And there's 20 or 30 years of people developing quite elaborate ways to simplify radiative transfer. Now we can do it line by line. And when you do it line by line, you can make some very simple assumptions, which almost like I did before, when you integrate over a line and you say, where is it optically thick, where is it not, which it's kind of a parameterization. You can come up with very simple things, and it allows you to understand what's going on at a rough level. But it doesn't have to be so detailed that you have to put it into a model and make it couple with everything else. You can get the main idea, and there I think we will advance faster because we will be focusing on the main concepts and not the engineering of linking the details of the concepts of a parameterization to details of other parameterizations. So I don't know if that made sense, but I think it allows us to begin thinking more conceptually about how processes work, and less in an engineering way, which is what happens when we have to put the parameterizations into models and hook them up to other parameterizations and things like that. So I think it will be an advantage. I'm not completely convincing. Some of my colleagues feel sad because they find it's much more interesting to solve the convective parameterization problem and have an elegant theory that works. But they've been working at it a very, very, very long time, and they haven't gotten very far in some measures. So, yeah. So I think that's how I think about parameterization. Yeah.
Yeah, thank you a lot for your question, for your answer. And I have another quick question. That is, as you mentioned, we may have the models at the resolution of 100 meters. I wonder, will it be difficult to carry out such simulations? Because when I conducted the simulations using WRF over the Tibetan Plateau, I found it is quite difficult to make even 2 or 3 kilometers with over the complex terrain. So do you think there will be some such problems?
Yeah, that's. I think there'll be a lot of problems. I think it'll be very difficult, and I'm not sure that we'll succeed. But that's why we want to do it, because in working through those problems, we will advance our capabilities greatly. So I think we can do it in a year and a half. There's some evidence that we can do it. For instance. A colleague in Japan ran the NICOM model for the atmosphere at 220 meters already, only for a few hours, but they were able to run at 220 meters globally. So that's still quite different than running for a month. Machines at these scales are terribly complex. You know, even the 1 kilometer thing, we get a huge number of nodes and we run, and then one node has a problem, or the memory wasn't flushed, this happens, that happens. You run a day, it crashes because some processor went blip. And so trying to get everything running to do a long simulations is an enormous challenge. But that's part of the reason why we're doing it, kind of also in the answer to this question, is really to try to, you know, if we can do it, then everything else that we do normally, just think, if we can run 100 meters or 150 meters globally for a month, running 2.5 kilometers suddenly becomes just like so easy. And it, you know, so it's really to burn the path, to move the path, and have great challenges that we can kind of motivate and excite people about.
Thank you a lot.
Okay, I think. And let's see, do we have questions from the online? No. Okay, then I give the last question to you, and because of time, yeah.
Thank you, Professor Bian. I have a little one question. For the development of the high resolution model, do we what type of resolution do you think is enough? Just like the story you told us about the kingdom and the map, the detailed enough map will be bigger, same as the real world. So, do you think the development of the resolution for the models is have an endpoint, or just like endless expectation?
Yeah. So I should, for instance, when we started running the models at 2 and 5 kilometers, I thought that some problems would go away that we've had that haven't gone away. So we have a problem of having a 2-zonal double ITCZ. And the Japanese have seemed to solve that problem, and they use techniques that we're going to try to see if it works for our model. But in our model, that problem didn't go away. If we go to 100 meters, I like to think that right now one of the difficult problems we have is the shallow cumulus over the ocean. And particularly over the Central Pacific, the shallow cumulus over the ocean set the albedo. And the difference between having too many clouds and too few clouds can be many tens of watts per square meter into the ocean.
the mixed layers are thin, and that affects the sea surface temperature. So the coupled climate is very sensitive in our model to these shallow clouds. Excuse me. So these shallow clouds, I think we will represent much better, and we will capture correctly. It depends then with the microphysics. Thank you. We still have to represent cloud microphysical processes, and we have ways. There's new ways. There's Professor Shima in Kobe University has developed new, better ways of representing microphysics that we can run at very fine scales. So again, we think that we will be able to get a handle on clouds and cloud microphysical processes. But the great thing about this and the great thing about research is that we don't know. We have good reason to believe that it will work, so we're not being silly, but we're really exploring unknown things. And that's kind of what makes research and science fun is, different people are exploring different directions and where we see where we can shine new light on things. So I think at 100 meters, we'll be able to do a reasonably good job on clouds which aren't precipitating. We'll be able to do a very good job on clouds that are precipitating. But I might be wrong. And the beauty about being wrong is it means that you learn something. You just don't want to learn stupid things. You want to learn something interesting. So, yeah.
Yeah, thank you. Thank you for your answer.
Okay.
Okay, because of the time, I think we have to conclude here. Before really concluding, we have still two things to do. Number one is that we are sitting here in the Institute for Carbon Neutrality, and the ICON Institute, which is a joint initiative in Tsinghua. I told you many institutions, and it's a marvelous new institution doing a lot of very good works. We also have a really high level. It's called a Climate Change Forum, which is really high level. We're happy to host you in this forum, and we have many science leaders being here to give talks.
Can I say a quick one thing about that?
Yes.
Because carbon neutrality, sometimes it comes up, people will say, well, why would you want to do such a big calculation? Because it takes so much energy and that uses so much carbon. And my answer to that is that there will always be energy intensive applications in the world. I think we'll always know there will be some things that we do which are making pharmaceuticals.
AI is such an example. AI is such an example.
Yeah. And
war is another.
War is another. Pharmaceuticals is another. Material production. So there are energy intensive industries, some which are good. And if we want to show how we can do this sustainably, then these sorts of simulations should be a joint project between the energy sector, developing methods to have energy intensive industries. So I think these are also ways to explore how to be energy intensive in responsible ways, because we have to show people how you can do it. And once we show them, then they will do it for all of these other things. So I also see it as a public showcase because of the carbon neutrality and because this all comes up. It's not that we don't think of that, but I think we have to use these public efforts to solve important public problems as showcases or demonstrators for how to deal with the fact that there will always be some energy intensive industries, and we need to give them solutions for how they can do what they need to do. So we can be a showcase too. So that's my way out of that problem.
That is excellent, because at Tsinghua we are also taking initiative to develop new energy program, which is really very big. And also at the moment we are also developing this in connection to climate change, because there are many new problems, there's new challenges, but also opportunities to do things better and to combine things like the energy consumption and also smart, more efficient, more resilient energy system and the climate change, for example. So excellent. And so what I want to say is that we have the institution here, ICON, and also my department, the Climate Forum. They have a gift to give to speakers in memory of you having here. And so let's hand over. Wow.
Oh,
So this is a memory for your office that you have been here to give this fantastic talk. Okay.
Yeah, thank you very much. It's really a pleasure. I should mention that the name of the model we use is called ICON, so it fits very well.
Oh, yeah.
That's good.
一次来看这里，非常看这里，哎，OK，OK，OK。